Welcome to Learn with us. This is the 24th lecture of Basic Electronics.
First, we will have a quick review of your previous lecture. In your last lecture, you understood configurations of transistors. You studied that there are three types of configurations. First is common emitter configuration, second is common base configuration, and third is common collector configuration. In your previous lecture, you also understood voltage amplification, in which you studied how transistors act as an amplifier. In your previous lecture, you also understood switching operation of transistors. You studied that transistors act as a switch in saturation and cutoff modes. What are the learning objectives of this lecture? In this lecture, you will understand application of transistor switch. You will also solve some examples related to transistors. In this lecture, you will also understand biasing schemes of transistors. Now we will understand a simple application of a transistor switch. The transistor is used as a switch to turn the LED on and off. In this case, the circuit diagram will look like this. The arrow is here, it means it is an NPN transistor configuration. Here we have RB, here we have RC, here we have VCC. This is a diode which is light emitting diode. Here we have input supply voltage. This input supply voltage is like this. Now, if this input is 0 volts, this transistor is in cutoff mode and there is no collector current. It means this LED does not emit light and it is off. Now, when this input voltage goes to its high level, this transistor comes in saturation mode and there will be some collector current. This collector current then flows through this LED and it causes it to emit light. It means now this LED is on. Okay, so this is how transistor acts as a switch and it will turn this LED on and off. This LED is off in cutoff mode and it is on when this transistor is in saturation mode. Okay. Now look at this example. If you have a transistor configuration like this, where the arrow is here, it means it is an NPN transistor configuration. Here we have VCC and for suppose it is 9 volts. Here we have RC and for suppose it is 220 ohms. Here we have RB and for suppose it is 3.3 kilo ohms. Okay, here we have VCE and for suppose here this voltage of LED is 1.6 volts. Now here we have input supply. If beta is 50 here, okay, so how you are going to find the amplitude of this input voltage which is necessary to make sure that this transistor is in saturation mode here. Okay, How you are going to start your analysis? First, we will find the value of saturated collector current. We know that the formula of this saturated collector current is VCC minus VCE saturated divided by RC. As you can see here in this collector terminal, this LED is also present. It means now this formula of saturated collector current becomes VCC minus VLED minus VCE saturated divided by RC. Okay, here this VCC is 9 volts, this VLED is 1.6 volts, and for suppose this VCE saturated is 0.3 volts here. Now we put this value here, and we know that this RC is 220 ohms. Okay, after solving this, you will get the value of saturated collector current, which is 32.3 milliamperes. Okay, now we will find the minimum value of base current. We know that the formula for this minimum value is saturated collector current divided by beta. This saturated collector current is 32.3 milliamperes, and here beta is 50. After solving this, you will get 646 microamperes. Now, in order to ensure saturation, we will use twice the value of this minimum value of base current. It means IB is equal to 2B minimum. Okay, and if we solve this, we get 1.29 milliamperes. Okay, we use this value of base current in order to make sure that the transistor is in saturation mode. Okay, now we will find the value of this input voltage, which is necessary to make sure that this transistor saturates. Here we know that base current IB flows in this direction, and we know that this is base emitter region where voltage drop will be VBE. Okay, it means here the formula of base current will be Vin minus VBE divided by RB. Okay, and if we rearrange this equation, we get Vin is equal to IB RB plus VBE. Here we know that IB is 1.29 milliamperes and RB is 3.3 kilo ohms, and in forward biased condition this VBA is 0.7 volts. After solving this, you will get 4.96 volts. So this is the amplitude of input voltage which is necessary to make sure that this transistor is in saturation mode. Okay, so this is your answer. Now look at this example. If you have a transistor configuration like this, where the arrow is here, it means it is an NPN transistor configuration. For suppose here this VCC is 10 volts, this RC is 4.7 kilo ohms. Here we have VBB, and for suppose it is 6 volts, and here we have RE, which is 3.3 kilo ohms. Okay, and we have voltage drop between these two terminals, VCE. Okay, if beta is 50 and you have to find all currents here, means you have to find IB, IC and IE. So how you are going to start your analysis? First we will find alpha. We know that alpha is equal to beta divided by 1 plus beta. Here beta is 50 and 1 plus beta will be 51. After solving this, you will get 0.99. Now, as you can see, there is no RB here in this terminal. It means here VBB will be equal to VB, because we know that VB is nodal voltage of base, which is here, and here it is equal to 6 volts. Okay, now we will find VE. We know that VE is nodal voltage of emitter, which is present here, and here we know that in this emitter base junction, VBE is the voltage drop, and VBE is equal to VB minus VE. In forward biased condition, this VBE is 0.7 volts, and we know that this VB is 6 volts here, and here we have VE. If we rearrange this equation, we get 6 volts minus 0.7 volts, which is equal to 5.3 volts. So this is your VE. Now we will find emitter current, IE. We know that IE flows in this direction. So the formula of IE will be VE minus VEE divided by RE. Here we know that VE is 5.3 volts because we calculated this VE in our last slide. Here this emitter is grounded. It means VEE is 0 and RE is 3.3 kilo ohms. After solving this, you will get 1.60 milliamperes. Okay. Now we know that the formula of IC is alpha IE. Here this alpha is 0.99 and IE is 1.60 milliamperes. After solving this, you will get the value of collector current, which is 1.58 milliamperes. Okay. Now we will find base current IB. We know that IB flows here in this direction. As you can see here, this VBB is 6 volts, and we know that VB is also 6 volts. It means this VBB and this VB, they are at same potential, so there will be no current flow here in this terminal. It means IB is 0 here. Now we will find nodal voltage at collector VC. We know that it is present here. We know that VCE is equal to VC minus VE. If this VCE is 0.2 volts, and we know that VE is 5.3 volts because we calculated it in our previous slides. Now if we rearrange this equation, we get VC is equal to 5.3 volts plus 0.2 volts, and it will give you 5.5 volts. So this is the value of VC. Here VB is 6 volts, VE is 5.3 volts and VC is 5.5 volts. As you can see here, VB is greater than VE and VB is greater than VC. It means this transistor is in saturation mode. Okay, it means it is on if it is acting as a switch. Now look at this example. If you have a transistor configuration like this, the arrow is here, it means it is an NPN transistor configuration. Okay, here we have a DC source, and for suppose it is of 5 volts. Here we have RB, here we have RC, and for suppose it is of 1 kilo ohms. Here we have VCC, and for suppose it is of 10 volts, and we know that the voltage drop between these two terminals is VCE, and for suppose it is 0.2 volts. Okay, now if beta is 50, then what is the value of this RB here? Okay, first we will find the value of collector current. We are not given any more values here, so what we are going to do, we will apply KVL in this region. Okay, now what will be our KVL equation here? It will be minus 10 volts plus IC RC plus VCE is equal to 0. Here we know that this RC is 1 kilo ohms and this VCE is 0.2 volts and it is equal to 0. And if we rearrange this equation, we get 9.8 divided by 1 kilo ohms. It means collector current is equal to 9.8 milliamperes. Okay, now what about base current? We know that collector current is equal to beta multiplied by base current. It means base current is equal to collector current divided by beta. Here collector current is 9.8 milliamperes and beta is 50. After solving this, you will get 1.96 into 10 raised to the power minus 4 amperes. So this is the value of base current here. Now here we know that the voltage drop between these two terminals is VBE, and here we know that VBE is equal to VB minus VE. As you can see here, this emitter terminal is grounded. It means here VE is 0 and we know that VBE is 0.7 volts. So if we put these values here, we get VB is equal to 0.7 volts. Okay, now for RB, we use this formula. IB is equal to VBB minus VB divided by RB. It means RB is equal to VBB minus VB divided by IB. Here VBB is 5 volts, VB is 0.7 volts and IB is 1.96 into 10 raised to the power minus 4 amperes. After solving this, you will get 21.93 kilo ohms, which is the value of RB. So this is your answer here. Now look at this example. If you have a transistor configuration like this, where the arrow is here, it means it is a PNP transistor configuration. Here you have VEE, for suppose it is 5 volts. This is RE, which is of 1 kilo ohms. Here we have RB, which is 10 kilo ohms. Here this VBB is grounded. Here we have VCC, which is minus 5 volts. Here we have RC, which is 10 kilo ohms. Okay, now if you want to find mode of operation here, and you also want to find all terminal currents, that is IB, IC and IE. So how you are going to start your analysis if beta is 30? Okay, first we will find base current IB here. For base current, we will apply KVL from terminals emitter to base. It means from here to here. Okay, and we start from VEE. So our KVL equation will be minus 5 volts plus IE RE plus VEB, because we know that in this region we have voltage drop VEB plus IB RB is equal to 0. Here we know that IE is unknown and RE is 1 kilo ohms, VEB is 0.7 volts, IB is unknown and RB is 10 kilo ohms is equal to 0. Okay, now we know that IE is equal to 1 plus beta IB. We derived this equation in our previous lectures. So if we put this value of IE here, we get 31 multiplied by IB multiplied by 1 kilo ohms plus 0.7 volts plus IB 10 kilo ohms is equal to 0. Okay, and if we rearrange this equation, we get IB is equal to 4.3 divided by 41,000. Okay, after solving this, you will get IB is equal to 1.04 into 10 raised to the power minus 4 amperes. Okay, so this is your base current. Now we will find emitter current IE. We know that IE is equal to 1 plus beta IB. Here 1 plus beta is 31 and IB is 1.04 into 10 raised to the power minus 4 amperes. After solving this, you will get IE is equal to 3.22 milliamperes. Now we will find collector current IC. We know that IE is equal to IB plus IC. It means IC is equal to IE minus IB. Here IE is 3.22 into 10 raised to the power minus 3 amperes, and we know that IB is 1.04 into 10 raised to the power minus 4 amperes. After solving this, you will get IC is equal to 3.116 milliamperes. Okay. Now we will find nodal voltage of emitter VE. We know that this is a PNP transistor configuration. It means here emitter terminal is here. Here we have VEE. Here we have RE. VE is here and IE flows in this direction. Arrow is here, and here we have collector terminal. This is RC. This is VCC, and here we have VC. Okay. Now here the formula of emitter current is VEE minus VE divided by RE, and if we rearrange this equation we get VE is equal to VEE minus IE RE. Here VEE is 5 volts, and we know that IE is 3.22 milliamperes and RE is 1 kilo ohms. After solving this, you will get VE is equal to 1.78 volts. Okay. Now we will find nodal voltage at collector. Here we know that collector current will flow in this direction. Therefore, the formula of collector current will be VC minus VCC divided by RC, and if we rearrange this equation we get VC is equal to IC RC plus VCC. Here we know that IC is 3.116 milliamperes and RC is 10 kilo ohms, and we know that VCC is minus 5 volts. After solving this, you will get VC is equal to 26.16 volts. Okay. Now we will find nodal voltage at base VB. Here we know that in case of PNP transistor, the direction of base current is like this. We know that here we have VB and here we have BBB. This is RB. Okay. So in this case, the formula of base current will be VB minus VBB divided by RB. Here this BBB is 0 because it is grounded. It means VB is equal to IB RB. Here IB is 1.04 into 10 raised to the power minus 4 and RB is 10 kilo ohms. After solving this, you will get VB is equal to 1.04 volts. Okay. Here VB is 1.04 volts, VE is 1.78 volts and VC is 26.16 volts. It means here VB is less than VE and VB is less than VC, and this is a PNP transistor. It means this transistor is in saturation mode. Okay, so this is your answer. Now we will understand biasing of transistors. There are three schemes to stabilize bias voltages of transistors. First is split power supply, second is two power supply, and third is feedback resistance RB. We know that DC bias sources are VBB, VCC, and VEE. The main purpose of biasing a transistor is to establish a constant DC collector current such that this collector current becomes insensitive to variation in temperature or large variation in beta. Okay. Now we will understand split power supply. The circuit diagram of split power supply looks like this. The arrow is here, it means it is an NPN transistor configuration. These two are connected to ground. This is RE, this is RC. Here we have VCC, again here we have VCC. This is RB1, this is RB2. Now, what are the rules of this split power supply? Here, first rule is VBB is equal to 1/3 of VCC. VCB is equal to 1/3 of VCC. This is second rule. Third rule is IRB1 plus IRB2 is equal to 0.1 minus 1 multiplied by IE. Here fourth rule is VEE is equal to 1/3 of VCC, and fifth rule is ICRC, which is equal to 1/3 of VCC. Okay, so these are the rules of scheme 1, which is split power supply. In split power supply, the formula of emitter current is VBB minus VBE divided by RE plus RB divided by 1 plus beta. Okay. Now we will understand second scheme, which is two power supply. In this case, the circuit diagram will look like this. Here we have VCC, here we have RC, here we have RE, and here we have VEE, and here we have RB, and it is grounded. Okay. Now in this case, the formula for emitter current will be VEE minus VBE divided by RE plus RB divided by 1 plus beta. Okay, so this is your second scheme. Now we will talk about third scheme, which is feedback resistance RB. In this case, the circuit diagram will look like this. Here the arrow is here, it means this is VCC, this is RC. Here we have RB, and it is connected like this. here we have VC, here we have VE, here we have VB, here IB flows here in this direction, IC flows here in this direction, and IE flows here in this direction. Okay, now in this case the formula of emitter current is VCC minus VBE divided by RC plus RB divided by 1 plus beta. Okay, so this is your third scheme. Now here is your class task. You have to use first scheme to design a transistor biased when IE is 1 milliamperes, VCC is 12 volts and beta is 100. We know that first scheme is split power supply and its circuit diagram looks like this. Here we have VCC here, VCC here, this is RC, this is RE, here we have RB1 and here we have RB2. Its equivalent circuit will look like this, where this is VBB, this is VCC, this is RC, here we have RB and here we have RE. Okay, so this is your class task. Take this RB very small for your initial analysis. Okay, that's all for today. Now what are the key takeaways of this lecture? In this lecture you understood application of transistor switch, where you studied how transistor is used to turn LED on and off. In this lecture you also solved some examples related to bipolar junction transistors. In this lecture you also understood DC biasing schemes of transistors.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.